Hey, I'm going to tell you about what is a motion map. Because we're going to do those sometimes. A motion map is just another way of representing motion. What are the different representations that we already know? Well, we could have we can have different ways of describing motion or different models. The word model and mode are related to each other by their etymological stuff. So that you could think of this as like different modes of representation. So what are the different ways? Well, I could just tell you about it. I could say something like cyclist A starts at 0 meters and travels in the positive direction with a constant velocity of 8 meters per second. That's like that problem we were looking at recently. So good old-fashioned words. That's one way to describe a model, right? A model is just like something that isn't the actual cyclists themselves, but is some kind of representation of them and what they're doing or whatever the thing is that's moving. We could do a table. So what would that look like here? A table would look like for, you don't have to put this in your notes, but if you were making a table here for the position of cyclist A and the times, you know this game, right, from your algebra days, so you could include as much or as little information as you want. So if I took times 0, 5, and 10, if I'm talking about the position of A, then this is time in seconds, this is position in meters, 0, and then at 5 seconds they're at 40, and at 10 seconds they're at 80. Right? You could do a table like that. That's a way to represent motion. It's a description of motion. You could write an equation. Equation of motion. So for this cyclist A, again, I could say, okay, so cyclist A, their position, that's what's on this axis. I'm writing a little a just because there's an A and a B there. Just helps me keep it straight, which one I'm talking about. So I'm thinking right now, I'm writing the equation for a line, right? This is a straight line. So I'm thinking y equals mx plus b, but I'm writing down the actual things that are going on here. So there's my, what's on this axis, that's like my y, equals m x plus b, the intercept is here is 0 meters. I'm just going to write it out. Right? So there's the equation of motion for this one. Just quick warning or heads up to you. The thing that I have seen more physics students leave out of this than anything else is this. Somehow I think that when we write down these units, some of us think that we've done the mx, the x part, but we haven't yet. This is the slope, and this is the horizontal axis variable, is t. Okay, so we have that. Like an equation. And then the other one that we're going to be interested in understanding is a motion map. So here's a motion map. Just give you an example. A motion map has, first of all, like a number line. It could extend past this in the negative direction like that. Sometimes we have them where if I know that I don't need anything into negative territory, I could do this. So there's 0, and let's see if I did. I'm going to stick with this cyclist A example here. Say I did 20. 40, this is 20 meters, 40 meters. You can scale this however you need to. for the context of the problem that you're working on. So I'm going to do this by 20 meters. And then you can also scale time. So what a motion map does is it shows by putting little dots along this where the object is as time goes by. So at time 0, that's where the cyclist is. So I'm just going to put a little dot there. And then what about at time, let's say time 5, if I wanted to do it by 5s, at time 5, and at time 10, we're there. So it's just another way of coding that information. So I want you to look at this table here, 0, 0, 540, 10, 80, and 0, 0, 540, 10, 80. It's the same information. The other thing we're going to do when we make a motion map is when we have this kind of separation of the dots, in other words, when something's moving, we're going to extend in the direction of motion a line that goes halfway to the next point. I don't want it to go all the way almost like that. It makes it too cluttered. Our convention, the way I want you to do it, is to go halfway to where that next point is. I'm not going to get out my my ruler and measure your little arrows, but just do your best to make them go halfway. Okay? So that's an example of what a motion map looks like. Let me give you a few more examples. And I'm going to frame those examples like this. What we would really like to be able to do is move comfortably between all of these different models, or all these different modes of our model. So in other words, if I give you a table, can you describe in words what's going on? If I give you words, can you come up with an equation? If I give you a motion map, can you do a table? Can you get from any one of these to any of the other ones? You could kind of think about this as, like, here's words, here's table, here's equation, and here's our motion map, not to be confused with Mr. McGrath. Can you move back and forth in any direction? Well, back and forth in any direction, I guess that's kind of redundant, between these modes. So there's actually a lot of different possible things that could happen, right? There's each one of these is two things. So 1, 2, 3, 4, 5, 6. There's 12 different ways that I could give you one of these and ask you for another one. I don't know. It's really not very hard once you get comfortable doing it, I think, and really just understanding what these are. So let me give you a couple examples. Here's I'll do a table. Here's times in seconds. Here's positions. We'll say in meters. Let's say something is at time 0. It's at position 1 meter, and at time 1, it's at position 3 meters. Time 2, it's at position 5 meters. Like that. Can we make a motion map? So do I ever go into negative positions? No. So I'm going to go ahead and start at 0 and just go this one way. And then how far do I go? Go to 7. So I think I could do 1, 2, 3, 4, 5, 6, 7. Right? Just make sure I have enough room. Here's 0, 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters, 7 meters. And you know, instead of doing that, I think I'd prefer to do this. So we'll say this is x in meters. All right, so where am I going to put my first dot? The first dot happens at time 0. So at time 0, I'm at position 1. Okay? At time 1, I'm at position 3. I always like to do a time 0, to do at least that first one, to mark that as time 0. And then at time 2, I'm at position 5. And at time 3, I'm at position 7. And please note that because we make a time 0 dot, that time 3 is actually the 4th dot that I'm making, right? Because we're starting time counting from 0. So make my little arrows there. Now, why am I not making an arrow here? You could make one. I'm not going to fuss at you about that. But I don't really know what happens after time 3, so maybe I'm just going to leave that one blank. If you want to make the next arrow, if that makes you feel better about the world, then please go ahead and do that. Okay, just for fun, now I've got a table and a motion map. Can we make the equation, and can we describe it in words? Sure. So how about words? We could say that the object, whatever it is, I don't know what it is, it's a cat. How about that? Starts at position 1 meter and travels in the positive direction at what's the velocity of this? Let's see, every second that goes by it moves forward to 2 meters every 1 second at 2 meters per second. And I mean, those are the key things, right? What direction? In other words, what's the sign of the slope? What direction is it going? What is the slope? What is the number, the actual quantity? And where did it start? And if you know those things, I mean, we basically just said what the equation is, right? Because remember from your notes that the general model for this is position is equal to velocity times time plus initial position. That's like what these equations are, right? Position is equal to velocity times time plus initial position. So if I know what the velocity is, it's 2 meters per second. And I know what the starting position is, it's 1 meter. That's my slope and my intercept, so I just need to put in my position equals this times time plus starting position. So there's all 4 of those. And give you one more example. This one I will do, go with words first. I meant to write an object, and I did a D there. I don't really know why that happened. An object, because there's no D's coming up in the word object, so don't know what's up with that. An object is at rest at position 5 meters for 5 seconds. And then it moves left at, let's say, 1 meter per second for 3 seconds. All right, can we make a motion map of that? So let's see. It's going to start at position 5, and it's going to go to the left, so I don't need anything past 5. So 1, 2, 3, 4, 5. That should be pretty good scaling. I'll say that this is position in meters. Then I don't have to write m's next to every number. Okay. Now let's see. It's at rest for 5 seconds. So it starts here. Now how do you do this if something is at rest? Well, you do it like this. It's not moving, so I'm going to stack up some dots. So there's time 1, 2, 3, 4, 5. So I want you to notice something here, that it's at rest for 5 seconds, but notice that there's 6 dots here. That's because like a second going by is the space in between these, right? If I just put that there, it hasn't been, nothing's happened, right? That's just like beep, that's just the start of time. So just keep track of them. If this is always start at 0, and then 1, 2, 3, 4, 5, and then it moves left at 1 meter per second for 3 seconds. So it's moving left, and notice how I'm lining these up now with that 5th one. So this is time 6, 7, and this is time 8, which should make sense to you that that's where we ended up, because if it did this for 5 seconds and this for 3 seconds, that's 8 seconds, so we should end up at time 8 seconds. So beep, beep, beep. Now, if this gives you, I don't want you to think here that it's like somehow moving down. The only reason we stacked up these dots like this is because we wanted them all to be at 5. This is an object that can only move back and forth along this line. So we're just putting these dots here because they're indicating this is the location, right? So it's staying still for those 5 seconds, and then it moves to the left. And I'm going to put in my arrows that go halfway to my dots. I'm not going to put one on the last one. Again, I'm not going to fuss at you if you do that. And there's my motion map. Good. How about we just make real quick a position versus time graph. Positions go from 0 to 5. Position is going to go on my vertical axis. And there's 8 seconds that go by, so let's see, if that was 8, cut that in half, cut that in half, cut those in half. This is time in seconds. Okay, so let's see, what happens here? For the first 5 seconds, it's just staying at position 5. So, first 1, 2, 3, 4, 5 seconds, it's at position 5. It's not moving. When you make this horizontal line, that's not a graph of something that's like moving this way. This is time on this axis. That is a graph of something that is holding the same position, constant position. And then it moves down. Eventually it gets down to 2, right? Position 2. And if you found the slope of this, the slope of that is -1, right? Because it's going this way, 1 meter every second. All right, that's how you do motion maps.